Okay. Anybody have any homework questions? Yep. Okay. Okay. Do anybody have it with? I bet Ellie does. What? Okay, so linkages number 4. Um, so we have a 3-meter long, 50-kilogram member. Like that. And then at the midpoint, there's a pin joint connecting that to a member with half the length. And it slides in a horizontal, that pin slides in a horizontal slot. And then there's a 800 Newton force at the end. I'll call the long one member 1, short one member 2. And I'll call this A, B, and C. The mass of member 1, the long one, is 50 kilograms. The short one is 25 kilograms. And we want to calculate the acceleration vector of 2 spots. Acceleration vectors of 2 spots. I'll call this D. We want to figure out the acceleration of the pin at C. And then we want to figure out the acceleration of the point D. It looks like I did not give the angles that you need, which is maybe what you were asking about. Okay, well, let's make up some angles. What is, I'm sure that is, the way that's drawn, I'm sure that's a specific angle in the picture. 20. Did I say that? You measured it? Yeah. Oh, okay. Oh, there's solutions for this one. Oh, okay. So, okay, well, great. That's the answer then. Okay, that should be said. Um, any other questions about that one, or that's about it? Okay. Well, then I'll just do the example I was going to do. Well, any other homework questions?
When you're using alpha 1 and alpha 2 in the constraint equations or when you're building those,
On a calculator? Okay. That's probably the best way, yeah, I suppose. If you have a TI-89 or an Inspire, you can enter alpha in the watermelon equation as a variable and it'll calculate it through. I think you have one of each model of TI calculator, so You just need to pick the right one. You should get like a tool belt. That would be cool. Oh, really? Okay, that's good to know. It doesn't do that. Okay, that's good to know. Um, that's sort of a pain, but yeah, I guess so. The answer is do the centripetal acceleration part by hand, and then use the calculator to do the omega part. Right. Yeah, that's good to know. I mean, I guess, yeah, it makes sense that there's some differences. All right, let's do the example I was going to do, and it's pretty similar to this one. Um, so we have a triangular shape. The triangle is an equilateral. Um, we have, just like in number 4 above, um, we have two joints with the ground. One is a pin joint, and then the other one is a pin and slot. But in this example, the slot is vertical, not horizontal. Um, I'll call this member 1, 2, and then the joints I'll do A, B, C. There's a external load of 600 newtons applied at joint B. The members are each 3 meters long. And both of them at this instant are at rest. So there's no angular velocity. There are going to be angular accelerations, and we're going to have to calculate those. And what we want to calculate is the acceleration of that pin at C. Um, so the basic, like the problem flow, we're going to start out by doing the rigid body problem, the rigid body kinetics for member 1 and member 2. Member 1 is going to give us one useful equation. Member 2 is going to give us 3 useful equations. Why the difference in the number of equations? There's a fixed point for 1, so we're only going to use the rotational equation. There's no fixed point for 2, so we're going to use both. Yep. No, those are up there. Oh, no, they're not. 10 kilograms each. Yes. I mean, unless there's 0. But the angular accelerations, like when we calculate them, could we make that a constraint, you mean? Okay. Yes, if that's going to stay an equilateral triangle, If it's going to stay an isosceles triangle, I guess this is the only place where it could be an equilateral triangle. Omega 1 and omega 2 have to be equal and opposite. But right now we're just saying that it's at rest, and then at that instant we apply this force to it. Okay, so we do the rigid body kinetics problem. We have 4 equations. Then we do the joint constraints. The first example we did last time, there was only one joint constraint. It was like the knee. This one, there are 2 joints, one at B and one at C. So there's a little more work to do in this problem. And then the last step is the acceleration of the point C relative to the ground is going to be equal to the acceleration of the point C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. The first term, the acceleration of C relative to the center of mass, is a circular motion problem, and the second one is one that we're going to have solved for with Newton's laws. Or it'll already be a variable. Okay, so first, body 1. Does that have a fixed point? Yep. So fixed. So A is A. And so that means that the mass moment of inertia, we're going to have to use the parallel axis theorem. So this is 1/12 times the mass times the length squared plus the mass times the distance from the center of mass to A. What's that distance? 1.5. And what do you get for this? 30? Wow. And then a free body diagram. The pin joint at A applies an unknown force vector. I'll call that the reaction at A. And then the pin joint at B, we have to decide which of these 2 members we're going to lump the pin in with. Okay. The way I always do it is I put it on the lowest numbered member, which means that the pin is part of member 1. So over here, we have the force vector on 1/2. We also have that 600 Newton force. That's, it's really applied to the pin, but our member 1 is that member and the pin. So 600. Our about point is here. And so the rho vector, force vector, moment vector. I will give $1 to whoever accurately guesses which step of this problem that thing is going to fall down on those guys. I predict it will happen during the joint constraint at C. Yeah. And the weight. Just kidding. sort of. I mean, I don't know if I'm. Uh, keep like I'll do like a step and then look up and be like, "Ugh," and then like go back to working. Ugh. Okay, so the mass is 10 kilograms. So the weight is 98.1. Uh, so first I'll do the force RA. Um, the row vector from our about point to that force is 0. I'm going to just write these all as 3D vectors. Um, so the force is RAX, RAY, and it's a planar problem, so nothing in Z. And then the cross product is 0. And then the weight force, the row vector there is, so this is 60 degrees. What's 1.5 times 0.866? Can someone calculate that? What? Okay, so 0.433 plus 0.866. Ooh, 1.299. Okay, so that's, which one is this? This angle is 30, so this is negative 1.299 and 0, negative 0.75, and then 0, right? The force vector is 0, negative 98.10. And what's the cross product? Zero, zero, 175 point, what, 127.5? 127.43 positive. And then the force F12, the row vector is twice this. So 2 point, negative 2.598 and negative 1.50. The force vector is F12x, F12y, 0. And what's the cross product there? Negative, oh yeah, negative 2.598 F12y plus 1.5 F12x, and 0 for x, 0 for y. And then the last one is the 600 Newton force. That also has the same row vector, negative 2.598, negative 1.50. Force vector is positive 600, 0, 0. And the cross product is 0, 0, 900. Yes. This has a fixed point, so no Newton's second law. Rotational equation says, so I'm just going to use the z components here. 127.43 minus 2.598 F12Y plus 1.5 F12X plus 900 is equal to the mass moment of inertia, 30, times alpha 1. And I'll rearrange that into our first equation for our system. 1.5 F12X minus 2.598 F12Y minus 30 alpha 1 is equal to 1027 point, this is going to be negative 0.43. Who's with me on that? And then member 2. Does that one have a fixed point? Nope. It has those joints, but no point on it stays in place. So no fixed point, and that means that our about point is going to be the center of mass. And so the mass moment of inertia about the center of mass is 1/12 times the mass times the length squared, and there's no parallel axis theorem part. So that is 7.5. And then the free body diagram. There's a weight force of 98.1. Up at the joint B where the two bodies connect, there's a pin joint. And so we have the force on 2 by 1, which is negative F12. What about the 600 Newton force? That's not there because we associated the pin with member 1. So that only comes through to this member in the reaction force. And then at C, we have this slot. We have this pin and slot joint. There's the slot, and the force is perpendicular to that. You know, there's nothing restricting motion this way, so there's no force. It only restricts motion perpendicular. You can draw that force whichever direction you want. I guess I'll put it in the positive x direction. That variable can come out positive or negative. I'll write that as the scalar RC. And then row vector, force vector, moment vector. Our about point is in the middle. So first I'll do this force negative F12, and I believe that row vector is negative 1.299, positive 0.750. The force vector is negative F12x, negative F12y, 0. No, that's right. And the cross product is 1.299 F12y plus 0.75. This is a component. 0, 0, okay. 1.299 F12y plus 0.75 F12x. And then the weight force is at the about point, so rho is 0. The weight is 0, negative 98.10. And there's no cross product. And then RC, the rho vector is 1.299, negative 0.750. The force vector is RC 0, 0. And so the cross product Z component is 0.75 RC. Do we use Newton's second law for this one? Yep, because there's no fixed point. So we have, I'm only going to use the X and Y components. Z component is 0 equals 0. So negative F12X, negative F12Y, plus 0, negative 98.1, plus RC 0 is equal to the mass of the body times the acceleration. I'll call that A2, and that is X and Y components. And then the moment equation says 1.299 F12Y plus 0.75 F12X plus 0.75 RC is equal to the mass moment of inertia times alpha 2. And this gives us our equations 2, 3, and 4. So equation 2 star says negative F12X plus RC minus 10A2X is equal to 0. Equation 3 star says negative F12Y minus 10 A2Y is equal to positive 98.1. And equation 4 star says 0.75 F12X plus 1.299 F12Y plus 0.75 RC minus 7.5 alpha 2 is equal to 0. Okay, so we have 4 equations. Before we count up the variables, anyone know how many we're going to have? 7, that's right. We had 6 when all we had was the knee joint. Now we have that extra joint that introduced one more variable, and that was that normal force RC. Okay. Variables now are F12, alpha 1, that's 3, A2, alpha 2, and RC, 2, 4, 5, 6, 7. That means we're going to need 3 constraint equations. But the increase in the number of variables that comes from each joint always matches the number of constraints on the motion that the joint provides. So even though we need more constraint equations than we did in the last example, we're going to have exactly the right number. So here's the deal. Here's how it works. This joint, because it's a slot joint, restricted motion along the x-axis. Okay. And so we're going to have one more constraint equation that just says the acceleration of this point C has to be 0 in the x component. Okay? The x component of that has to be 0. But along with that extra constraint came the force that enforces that constraint, which is the normal force saying you can't go horizontally. Okay. So that's why you always have the same number of variables that you have equations after the constraints. Okay, so first I'm going to do the constraint at B. And that just says that the constraint, that the acceleration at B, according to member 1, has to be equal to the acceleration at V, according to member 2. So we have to calculate the acceleration according to each of these 2 members. And then once we get these expressions, we'll set them equal. Any questions about where we're going? Okay, so first, member 1. The acceleration at B, according to member 1, this one has a fixed point, so we don't have to use relative motion. It's just circular motion around that fixed point. So we have 0, 0, alpha 1. Passed with the r vector from the center of the circular motion to the point in question. So that r vector, this point P is moving in circular motion around A. So that has to be negative 2.598. Negative 1.50. And then for circular motion, we add on this stuff. But we were given in this problem that it's at rest at this instant, so that goes away. So this is all we have to worry about. So we have, for the x component, 1.5 alpha 1. For the y component, negative 2.598 alpha 1. and 0z component. And now member 2, this one doesn't have a fixed point, so we're going to have to use relative motion. So the acceleration of B, according to the ground, is equal to the acceleration of B according to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. And so this says the acceleration of B is 0, 0, alpha 2 crossed with the r vector from the center of mass of 2 to the point we care about. So that's negative 1.299, positive 0.750, plus the centripetal part, which is going to go away. And then the relative motion part, the acceleration of the center of mass of 2 relative to the ground, is the variable that we're calling A2. And so for the x component, we have negative 0.75 alpha 2, bless you, plus A2x. For the y component, we have negative 1.299 alpha 2 plus A2y, and then zeros for z. And now we just set those two equal to each other. This one equals this one, like a long equal sign. Okay, so to put these in the equations, I'm going to say the acceleration of B according to member 1 minus the acceleration of B according to member 2 is equal to 0. That's setting them equal. So our equation 5 star says, I keep forgetting this, 1.5 alpha 1 plus 0.75 alpha 2 minus A2x is equal to 0. And then equation 6 star says 2.598 alpha 1 negative plus 1.299 alpha 2 minus A2y is equal to 0. Any questions about that? Okay. So now we're done with the constraint at B. We need one more equation, and that's going to come from the constraint at C. Now I have to slow down a little and just to give that thing a little time to work itself loose. So for this one, we just have to calculate the acceleration of that point C according to member 2. The acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And so I'll rewrite this as the acceleration at C is equal to 0, 0, alpha 2 crossed with the r vector. This time our r vector is going from the center of mass of 2 to C. So that is positive 1.299, negative 0.750. And then, generally it would be plus omega 2 cross quantity, omega 2 cross r. But since this thing is at rest at this instant, that's 0. And then plus the acceleration of the center of mass according to the ground, which is our variable A2. So the acceleration of that point C is 0.75 alpha 2, 1.299 alpha 2, 0 for Z, and then I forgot to add on the acceleration. So for the X component, add on A2X. For the Y component, add on A2Y. Okay, and that's the acceleration of C. Okay, so how do we use this now for a constraint? What's the constraint we want? We want the X component to be equal to 0. So we don't care about that Y component of the acceleration. In fact, that's what we're going to try to calculate in the end. But we want to take the X component that we just calculated and set it equal to 0. So equation 7 star says 0.75 alpha 2 plus A2X is equal to 0. And that's just saying that the acceleration at the point C, X component is equal to 0. Okay, so to solve this, this is 7 equations for 7 variables now. We need an equation with 7 rows and 8 columns. A matrix, I mean, with okay, so that's 7 rows, 1 for each equation. There's 8 columns. And the variables are f12x, f12y, alpha 1. And then I guess I'll do it RC, A2x, A2y, and alpha 2. And then the constants. So now, can someone read me? So go back, we're just going to go through those equations one by one and tell me what variable is non-zero and read me the coefficient. So first equation 1. You're all like, we were only pretending to write this down. Okay. Okay. Negative. Oh, there's so many numbers. Yeah, negative. Okay. Equation 2. Okay. Yep. Okay. And then negative 1 f12y, negative 10 a2y. Okay. 4. 1.299. Okay. 0.75 RC. Negative 7.5. Okay. 0. Okay. 1.5 alpha 1. 0.75 negative 1 a2. Okay. 2.598 alpha 1. 1.299. Okay. Negative 1 and 0. Okay. Oh, and I can see the last one. Alpha 2.75, A2x 1 and 0. Ooh, let's solve it. We still have time. So F12. Mm-hmm. Okay, negative. And I'm going to allow, so we have a negative 2.6 in equation 1 and a negative 2.596 in equation 2, 598 in equation 2. I'm going to allow that because it would make the chemistry professors so mad. Exactly. What I mean, yeah.